Welcome to the second half of Semester 2 for Unit 10 Maths for Business. This is the financial maths part, and although there's lots of higher mathematics going on in here, most of it we just brush on a little bit. Geometric series, logarithms, that kind of thing comes in just to the extent that we need it in order to calculate specific things. Most of it boils down to a firm grasp of how percentages work and how we can describe them and work with them as percentage multipliers. That's an idea that I'm going to get into in just a moment. Specifically, what happens in the very first section of this course, percentage increase, decrease, and reverse percentages. This is to do with how we can, with one single operation, multiplying by a single number, we can change a value by increasing it by a certain percentage of itself or decreasing it by a certain percentage of itself. We'll find that comes into all the other things. When we're talking about compound interest, it's a case of repeatedly increasing by a certain percentage. So we can treat that as a power of a percentage multiplier. If you want to increase something by 5% for 12 years, you multiply by 1.05 to the power 12. And we'll see how that works shortly. So if you are unfamiliar with calculating percentages with a calculator, or if your method takes more than a single step, then this is going to be really important to pay attention to. When we have a percentage written as a percentage, what it means is instead of 73%, you need to convert it from Latin to English in your head. It's 73 out of 100. That's what percent literally means. Even the percentage symbol comes from a squashed version of dividing by 100. So when you see 73%, what you're looking at is a number which is bigger than 0, but it's less than 1. It's between 0 and 1 because it's between 0% and 100%, 100 out of 100. And 73% is more easily written and thought of as 0.73 when it comes to calculators. Now, 21% turns into 0.21 and 40% into 0.40, which is the same as 0.4. But a lot of people will start to think they see a pattern and then extend the pattern to 4%. But you should notice that 0.4 is what 40% gave us. So for 4%, we're going to need to do 0.04. A good way to make sense of this in your head is to remember that percent is not just telling you to get rid of the percentage sign and put a 0 point in front. It literally means to divide by 100. So take the number 4, divide it by 100. So divide it by 10, you get 0.4, divided by 10 again, 0.04, and that's what you're looking at. With 99%, you should get 0.99, which is very close to 1, because 99% is very close to 100%. 2.5% will not give you 0.25, that's actually a quarter, that's 25%. 2.5% will be a bit bigger than 2%, so it'll be a bit bigger than 0.02, which means it'll be 0.025 in this case. 0.001 for number 7, and then 1.23 for question 8. In some situations, people say that percentages bigger than 100 don't make sense. It doesn't make sense for a football player to give 110% of his effort. And there are various other situations where it will be illogical. Your phone can't charge up to more than 100% of its battery power because by definition, its maximum capacity is what the percentage is measuring in relation to. But it's perfectly possible to spend 123% of your income. It just means you'll be in debt at the end. House prices can rise as well as fall. And if the house price has risen by a sufficient quantity, then you could compare it to its previous value, and potentially it's not just increased by 20% or 50%, it may have increased by 105% or more than doubled, and that's what a percentage like 123% might come in the context of. Often though, what we use it for is to calculate a percentage increase. If I have all of something and then you give me a bit more of that thing, if I have £1,000 and you pay me 5% interest, so you give me £50, now I have £1,050, which is 105% of what I had. That's what we're going to get onto next. But first, calculating a percentage of something in order that we can work out how to find a percentage increase on something. So when you do a percentage of something, you can turn it into a situation that the calculator can understand by replacing the percentage with a decimal that represents the same number, and then we write times or multiplied by instead of. This is the same logic behind when we say 3 boxes of 4 eggs or 3 lots of 4 eggs. You would do 3 times 4. If you say a half of 12 on a calculator, that looks like a half times 12. So it does exactly the same thing. 51% of something is a bit more than half of the something. So you do half times, or in this case 0.51 times 200. Another good tip to be aware of here is that you can check that your answers are sensible. Question 8, 150% of £3. That's more than all of it. The answer should be bigger than the original number. Whereas 93% of 332, that's less than the original number, but not much less, because 93% is quite close to 100%. Here's a few more examples that you can do with the calculator. You'll notice with 34%, it becomes 0.34, the £260 remains 260, and you multiply by it. The only concession we have to the pound sign is that once you've got an answer of, say, 88.4, you remember that the original quantity, the thing in blue, was measured in pounds sterling, so our answer, in this case, will also be in pounds sterling. So the same sort of thing happens with the rest. Remember, if you've got a small percentage, like 2.4%, you'll have a very small amount at the end. If you have 2.4% of £876.50, you'll end up with £21.04. So not a completely unimportant amount, but pretty insignificant compared to the original quantity. And with question 4, finding 120% of 11,000 is equivalent to finding a bit more than all of 11,000. And this is what we're going to come to when we start looking at a 20% increase. First though, combining percentages. The example here is an employee discount followed by a sale. First of all, it seems fairly logical. If you buy the shoes today before they go on sale, well, you get a 30% discount, so you'll be paying less than you would otherwise need to. If you wait and you buy them in the sale, then you end up with a 25% discount. If you're allowed both the 25% discount and the 30% discount, it turns out it doesn't matter what order you apply them in. This is one of the interesting consequences of the fact that finding a percentage is equivalent to multiplying by something. There is a particular scale factor, a ratio if you like, that you're multiplying a number by when you apply a percentage increase or decrease. When I say I'm decreasing the price of something by 50%, that's equivalent to just getting half of that thing. I've lost half, I'm left with the other half. And that's the same as multiplying by 0.5. Now I can multiply in this case by 0.75 to reduce the price by 25%. Then I can multiply by 0.7 to reduce the price by 30%. But the overall effect is equivalent to multiplying by 0.7 followed by multiplying by 0.75. So for the first part, you save a certain amount and you end up having to pay only £56. The second one, you buy them in the sale after the 30% discount is applied. You end up needing to pay even less. But you'll notice that 30% of £60 is not as much as 30% of £80. Either you get a large discount because it's 25% of a large amount of money followed by a smaller one, or vice versa. But at the end of the day, it comes out exactly the same. So those two numbers are not going to change. That's a really important idea. It means that if you're applying a series of percentage change multiples, it doesn't matter how you do it. If you're handing over a bunch of coupons for various compounding discounts, the order in which those get applied makes no difference. Now, if I want to increase something by a percentage, the important way to think about this is to imagine you want all of what you've currently got, and you also want an additional, in this case, 34%. Start with the whole thing and add on 34%. Well, what you've already got, the whole thing, 1 of £600, that's 100% of £600. If you have another 34% of £600, then you have 134% of £600 altogether. This is what allows us to do this calculation in one single step. 34% increase means you need to end up with 134% of your number. You could work out 34% by doing 0.34 multiplied by 600, and then you could add it on to 600. But because that ends up being 2 steps, it's very hard for you to generalize that if you need to do it 10 times in a row. It's very hard because you'll be multiplying and then adding. Then you'll need to multiply again, get a different number, add it on, and so on. If we can turn this into a single multiplying step, not only can we do it repeatedly, very easily, we could also reverse it by doing the exact opposite of multiplying by 1.34, which we'll get to in a moment. To do a decrease, it's a similar idea. We start with all of it, and then we change from there. So in this case, you start with 100% of 600, and you decrease that by 34% of 600. So all of it minus 34% of it. And what you're left with there is 66% of it. So you turn that into a decimal and multiply. The decimals that I refer to when we're talking about percentages, I call them percentage multipliers because that is almost always what you're doing with them. In fact, although it may seem strange, whether you're increasing or decreasing or just finding a percentage of something, you're always multiplying by something. If you want to find 14% of something, you multiply it by 0.14 because that's 14%. To increase by 14%, you want to find 114% of it. So that's 1.14. If you start with all of it and you decrease by 14%, then you've dropped down to 86%, so you need to work out 0.86 multiplied by the value. If you're finding 2.4% of something, and that keyword is of, we have 2.4% of a number, you just turn 2.4% into a decimal and multiply by that. If you want to increase, you start with 100% and you add on the additional part. So with this one, increase by 114%, that's going to be more than doubled. You're adding on more than you currently have. If you have 100, you're increasing by another 114. You'll be left with 214. That's 2.14 times what you had before. So the logic is exactly the same as in the blue box here. You increase all of it by a certain amount, and whatever you end up with, that is the percentage multiplier. For decreasing, you would never decrease by more than 100%. You're not going to go negative in this case. If we decrease, we go down to a small portion of whatever we had. So a significant decrease, like a 92% decrease, means you're multiplying by a very small number, in this case 0.08, because that corresponds to 8%. There's a few other questions here involving increase and decrease, and there's lots of resources on LearnZone, including a spreadsheet that will auto-generate new questions for you if you need lots of practice on this. To decrease by 15%, you need to multiply by 0.85. Think of it as you need to find out what's left, the 85% that's left over after you've got rid of 15%. Similarly, for 20%, you're left with 80%. If you want to increase by 50%, you start with all of it, and then you add on another 50%, 150% or 1.5. The next one is an increase from 100% to 165%, so 1.65. If you decrease by 40%, you start with all of it, and you lose 40% of it, you're left with the remaining 60%. And the rest are similar. You can look through these at your leisure. Question 11 is the first one that starts to look like financial mathematics properly. £3,000 is invested in a savings account for 1 year at 5% interest. Increase £3,000 by 5% to work out the overall total after a year. That is exactly what interest means. When interest is applied to an amount of money in a bank account, or even to the amount of debt on a credit card or on an overdraft, what happens is the total amount increases by a certain amount. If it's debt, that's not a good thing. You're now in more debt. If it's savings, that is a good thing. You now have more savings. But whether it's debt or savings, it's a bigger amount. So if £3,000 is saved at 5% interest, it will be 5% bigger by the end of the year. To increase by 5%, you multiply by 1.05. If we have 20% tax, you are decreasing something by 20%. So in this case, that was a £30,000 salary. You lose 20% of it, that much is paid off as tax. You're left with the remaining 80%, so you'd multiply by 0.8. And if you want to check the actual values you get when you apply the calculations, they'll be on here as well. These are more wordy questions. What tends to be the trickiest thing here is making sense of exactly what's being asked. But if you get it clear in your head that there's just a handful of common things that you'll be looking for, you're either calculating a percentage of something, or you're finding a percentage increase, or you're finding a percentage decrease. If you invest £3,000 at 4%, then you'll have 4% more at the end of the first year. So you're multiplying by 1.04. If you reduce something by 15%, you'll be left with the remaining 85%. If you put money in a bank account and get 3.5% interest for a single year, then you increase the value by 3.5% to 103.5%, 1.035. To reduce by 12%, you find 88% of the original value. To increase by 9%, you find 109% of the original value. The next question involves the word depreciates. Just like interest has an in for increase, depreciate has a D for decrease. So that's a bit of a clue that this is going to be a number going down. But it's even more important that you understand the concept behind it. When you buy a car, generally speaking, it is worth less when you've had it for a year than it was when you first bought it. And this is true whether or not you buy new cars or second-hand cars. If you buy a car for £1,000, like I did 10 years ago, then by the time you finally sell it, which I did 1 year ago, it's worth a lot less than £1,000. My car had reduced from £1,000 to about £200 scrap value by the time I got rid of it. So the concept of depreciation is that the car loses a certain amount of its value every year that you have it. And from a business perspective, you would take that into account by making a note in your accounting records that you have lost a certain amount of your assets. You still have the car at the end of the year. Let's say it was worth £1,000 at the start of the year and it's now worth £800. So you can write off £200 worth as the cost of having the car for a year. That avoids you having to think about spending £1,000 as a one-off in 1 year, but then not spending any money on buying a new car for another 10 years. If a car depreciates by 20% each year, then all you need to do to apply that depreciation is multiply by 0.8. We have a duplicate question there, so you can ignore that one. For question 8, Pat normally pays £45, but the fares are increased by 9%. So we multiply by 1.09. If a radio costs £46.80, but we're going to increase it by 17.5%, that's why it says plus VAT. VAT is value added tax, that's the sales tax in the UK. Then we multiply by 1.175. These days VAT is 20%, which makes for slightly nicer calculations. Again, these are the exact values you get if you calculate those. And you'll notice that in some cases, they're given with pennies rather than just whole pounds. In that case, it's likely that they've been rounded as well. So you'd usually round to the nearest penny, or possibly even to the nearest pound, but you wouldn't give a more precise answer than that. This next bit is to check your understanding in terms of increases and decreases and what happens with different values. So whenever it's an increase, you are adding that percentage to 100%. And you will always end up with multiplying by something bigger than 1. Which makes sense. If you multiply by 1, things stay the same size. If you multiply by something less than 1, like 0.5, they get smaller. And if you multiply by something more than 1, not just 2 or 7, but also 1.3, for instance, then they will get bigger. A decrease by 30% will get smaller. In this case, it will become 70% of whatever size it was before. If you increase by 3%, it's not as big a change as increasing by 30, but it is 103% of what it was. Increase by 300% means that whatever you had before, you now have another 3 times as much. Altogether, you have 4 times as much as you had. To decrease by 0.3, you need to subtract 0.3 from 100. You get 99.7%, which is why it's 0.997 as a multiplier. The last one is the one that's most useful here, I think. Increase by 15% twice. You'll notice that if you do multiply by 1.15 and then multiply by 1.15 again, what you find is you don't get the same as if you just multiply by 1.3. Increase by 30% and increase by 15% twice are different things. They have a different effect, and that's because the second time you apply the 15% increase, you're applying it to a slightly bigger number. So you get interest on the interest that was already paid. That's essentially what's happening. And we'll look at that in more detail soon. There's a few additional questions on here that you can try. They're similar. One of the differences you'll find with the smaller text here is they ask questions about how much something is worth after a number of years. For instance, £3,000 earning 3% interest, how much is it worth after 4 years? You would consider the 3% interest as a 1.03 multiplier, but to apply 4 years worth of interest, you can either multiply by 1.03 and then multiply by 1.03 again, and then again, and then again, or you could have 3,000 multiplied by 1.03 to the power 4. So here's what that would look like for these. This is 3,000 times 1.03 to the power 4 for question I, and similarly for the final 3 questions, if you have a 1.5% increase for 3 years, you multiply by 1.015 to the 3. If you have a 1% increase for 5 years, you multiply by 1.01 to the 5. And if you have a 12% decrease for 5 years, you multiply by 0.88 to the power 5. All of these have the same effect. They'll be repeatedly applying the same proportional change. Now, debt can be one that confuses people. We think that because when you're in debt, you end up with less and less money, that it's somehow a percentage decrease. But the thing to remember is the amount of money that you owe is increasing. It's still called interest, it's still increasing. And 20% per annum means for each year that goes by, the debt will increase by 20%. That means that after 1 year, you have a 20% larger debt. After 2 years, it's larger still, and it's grown slightly more than it did in the first year, because you're not just paying interest on the 6,125 now, you're paying interest on the 7,350, the extra 1,000 and more pounds that you now owe them because they charged you interest. You now need to pay interest on that. You'll notice how this rapidly gets out of control. I can't remember who it was who said it, possibly Einstein. Compound interest is the 7th wonder of the world. He who understands it earns it, he who doesn't pays it. This is what happens when you have a 20% interest rate. Usually you never see a 20% interest rate unless it is associated with a debt. You will be paying a 20% interest rate. If you borrow 6 grand on a credit card and then forget about it for 5 years, you will owe more than twice as much as you originally borrowed. After 10 years, it gets bigger still. You want to watch out for debt that grows this fast. Savings, on the other hand, they don't grow anything like it so rapidly. If you have £7,000 in savings, even with a reasonably good interest rate, you're unlikely to get the kind of returns that you would see if you had a 20% increase. So it's still technically exponential growth. The value is growing at a rate which is itself accelerating, but you rarely see savings grow as fast as debt because the interest rate on savings will typically be very low. Currently in the UK, the interest rate is less than 1%. and even if you've got a really good savings bank account, you're unlikely to get more than 1 point something %, possibly 2 if you're lucky. Whereas overdrafts, loans, credit cards, they can quite comfortably charge 15, 20, 30 or 40%. And if you get a payday loan, then because they tend to be more short term and you pay them off more quickly, the APR is not necessarily the best way to measure it, but if you did measure it in terms of an annual rate, it will be equivalent to thousands of percent APR. This coupon comparison comes back to one of the ideas we had earlier. If you apply repeated percentage changes, the effect is not changed by the order in which you apply things. But there's another thing going on here. 50% off plus another 40% off makes it sound as if you have 90% off. But if you actually crunch the numbers, you find that the overall effect is equivalent to a 70% off, which seems very strange. But if you try it out with a number, it makes more sense. £100, knock off 50%, you're down to £50. If you knock off 40% of 50, well, now you've just lost £20, or you've saved £20, I suppose, so you end up with 30. The 40% off doesn't have such a big effect when it's having its effect on a smaller amount. So in this case, you'd be better off with coupon number 2. You'd save 75% instead of only saving 70%. And that's true regardless of the price. I was able to do this without even thinking about £100 by considering the effect of a 50% decrease followed by a 40% decrease and just combining the two multipliers together. This one looks even more contradictory. If you get 25% off 5 times, surely you end up going into negative numbers. Well, think of it more like this. If there is a cake on the table and you go to the cake and you take a quarter of the cake, and then you come back to it a bit later and you take a quarter of what's left, you get a slightly smaller slice. There wasn't as much there the second time as there was the first time. And if you come back again and take a quarter of what's left, and again a quarter of what's left, there's no limit really, apart from till you start getting to impossibly small crumbs. You can continue to take a quarter of whatever's left, and you'll just get smaller and smaller amounts. You'll leave smaller and smaller amounts behind. So in this case, although it might look like we end up reducing down to 0 or negative 25%, what's really happening is it's a 25% decrease followed by another 25% decrease, which will have a smaller impact, followed by another and another. And at the end, 0.75 to the 5, which is 5 25% decreases back to back, that's equivalent to multiplying by 0.237, which is a 76.3% decrease, because you're left with only 23.7% when you started with 100%. There are a number of questions on LearnZone that you can work on using repeated percentage change. You can do an increase for a certain number of years, like at the beginning of question 1, or a decrease for a certain number of years. You can do an increase followed by a decrease. You can mess with the values. All it takes is a correct combination of multipliers, and the overall effect you can work out and write down as a single decimal, and that itself will give you an indication of what the percentage change is that it represents. When we consider an increase of 40% followed by an increase of 20%, we can test those two by considering what happens when we multiply by 1.4 and by 1.2. If you do 1.4 multiplied by 1.2, you end up with 1.68, I think. In other words, you get a better result by increasing in 2 separate chunks than you would if you increased all at once, if you like. For the next one, you have a 5% interest rate applied twice, and then a 7% interest rate applied 4 times. And at the end, you have depreciation, so you're reducing by 35% for 3 years. Next, we have some more repeated percentage change problems. If you worked on these, we've got answers for these as well. You'll notice that it doesn't matter how many years you want to apply an interest rate for, because of powers, you can really efficiently write down any of them that you like. 20 years, you use a power of 20. 150 years, use a power of 150. You don't have to sit there pressing your calculator equals button multiplied by 1.05 and trying to count how many times you do it. You can use powers and it makes the entire process a lot quicker. If you increase by 16% and then you decrease by 4%, the overall effect can be calculated by multiplying the multipliers together. And for question 3, one way to calculate this would be to start with £3,000 and repeatedly multiply by 1.04. If you do that over and over again and count how many times you do it, you'll be able to keep track of how long that needs to happen for until the value reaches 4,000. There are more efficient ways to answer that question, and we'll get to that when we come to logarithms. Similar thing happens with question 4. The Lifetime ISA in the UK is a tax-free savings account designed to help people save for a long-term goal such as buying a house or retirement. The government boosts whatever savings you put in by 25%, but if you change your mind and decide to take the money out before you retire or you spend the money on a house, then the government will reduce the balance by 25%. It sounds fair, it seems reasonable, they gave you the 25%, surely they can take it back. But if you try working through with the numbers, if you increase 4,000 by 25% and then decrease the resulting 5,000 by 25%, you end up with a little bit less than the 4,000 you put in. And I think it's a bit sneaky. I think they've deliberately chosen 25% because it looks like they're taking from you exactly what they put in. But in reality, the 25% that the balance is reduced by at the end is 25% of the new increased total. So they take more from you than they gave you initially. You can work out exactly what the effect is by multiplying the two multipliers together, 1.25 and 0.75 multiplied together. And you'll find that you get approximately a 6% decrease if this is what you do. Can you reverse a percentage increase with a decrease? Every single question we've done so far, we've been multiplying by a percentage multiplier. Sometimes by 1 point something, sometimes 0 point something, occasionally even bigger than 1 point something. In this case, we have a situation where you increase prices by 50%, followed by a decrease by 50%. If you try applying these, you'll find that the ticket prices do not go back to what they were before. In fact, the overall effect is that the price has dropped. This is because the original 50% is implicitly 50% of £2, and that increases the price to £3. Once we decrease the prices by 50%, you're decreasing by 50% of £3, which means they drop down to just £1.50. Reverse percentage change, therefore, we need a different method for this. If you want to reverse multiplying by 0.75, a 25% decrease, you can't do it by multiplying by 1.25, a 25% increase, because they don't cancel each other out. But there's a nice, easy shortcut for this. The opposite of multiplying by anything is dividing by that thing. In question 1, prices are reduced by 25%, which means they've been multiplied by 0.75. And the result is that a dress now costs £30. How much did it cost before we multiplied the price by 0.75? Well, divide 30 by 0.75 and it'll tell you. This is the essence of a reverse percentage change. Take your value, divide it by the percentage multiplier that would have produced it, and you've got your result. You can check your answers on here. The other important thing about this, reverse percentage change is always harder to get to grips with than an ordinary percentage change. So if you've got a value and you think it's right, try applying the percentage change in the ordinary direction and see if your answer makes sense.